A potentiometer with this configuration can be described by the circuit like this diagram here. So we can actually describe the intersection of the output terminal with the resistor to be at point C, which we can see as a separation point for two different resistors with R ohm and capital R minus R ohm. So with this configuration, it's pretty obvious that the output voltage at this point is going to be given by this expression, where it's nothing more than small r divided by capital R multiplied by the total voltage applied across the potentiometer. Let's look at the questions. So if we wish to measure the current flowing through the lamp, then we have to put the emitter in series configuration. So we can either put our emitter here or here. And if we wish to measure the voltage across the lamp, then we need to set up a parallel circuit with the voltmeter attached. Then only we can measure the voltage across the lamp. And when the sliding contact S move from terminal P to terminal Q, then as described by this equation here, we know that the voltage that we apply across the lamp is going to go from maximum to minimum. So the brightness of the lamp is also going to be going from maximum brightness to minimum brightness, which is dark, all the way dark. Alright, and then the lamp is marked with 12 volt and 200 milliamp. So this is the normal operating point for the lamp. And then it also says that when the supplied voltage range from 0 to 1 volt, then what happens is that the resistance of the lamp has a constant value of 11 ohm. So it seems like the resistance of the lamp is not constant all the time, and it's understandable because as we learn from physics, when a conductor, especially a metal conductor, when the temperature is higher, then what happens is that the resistance is also going to be higher. So when the lamp is operating at the normal operating point, there will be more current flowing through. And if we calculate the resistance under the resistance of the lamp under the normal operating point, then we need to divide the voltage by the current, and then this will give us 12 divided by 0.2, and there will be 60 ohm. So we can see that the resistance of the lamp actually increased by a factor of 6 when the lamp is operating at normal point as opposed to 0 to 1 volt. So for the first part, we need to calculate the current in the lamp when the PD across is set at 1 volt. So when the voltage is at 1 volt, and then it's given that the R is equals to 11 ohm, then current is given by V over R. So in this case here is given by 1 over 11, and this is nothing more than 91 milliamp. Alright, so for the second part of the questions, we need to sketch a graph to show how the current in the lamp changes with the PD across it. So let's roughly sketch the graph. My drawing is not very good. Okay, let's first put on the important point first. So the maximum current is 200 milliamp, and then this is what? This is the PD voltage, and then here is a zero intersection point, and then it's given that. And one more thing to point out is that because this is a IV curve, so the gradient is given by I over V, and this is nothing more than the inverse value of resistance. So, and we know that the resistance will be increased when the voltage of the across the lamp is increased. So the curve would look something like, at first it's going to be pretty linear as described by the given information. For the 0 to 1 region is only 11 ohm, so it's going to increase linearly up to 1 volt, and then this is the point that we just calculated, which is 91 milliamp. And we also have this information when the lamp is operating at the normal operating point, which is 12 volt and 200 milliamp. So at 12 volt is 200 milliamp. So these are the information that we have, and apparently the resistance of the lamp is not going to be linear across the diagram. So what happens is that it's going to grow like this, simply because the gradient of the curve is going to be smaller and smaller as the resistance get larger and larger. That's all.